Welcome back, students. In this video, we are going to continue with the problem of design of gantry girder. In the last video, we discussed what are the different types of loads that a gantry girder experiences, and we calculated the vertical load, the wheelbase load, the lateral load that is coming onto the gantry girder, and the corresponding bending moments and shear force, right? So in this video we are basically going to extend the problem, and by using the calculated loads, bending moment, shear forces, we are going to now design the gantry girder. Okay, so let's get started. All right. So before we begin, there are a few things that you need to understand. Gantry girder is not a regular beam or a plate girder. All right. It has certain specific conditions, like since it is carrying a railroad, it is laterally unsupported throughout. So you have to check the lateral, whether the beam is safe under that condition or not. And along with that, it also has lateral loads coming onto it. So in certain cases, you have to you have to check the combined effect of certain loading condition taken into account, right? Usually what we do, usually in case of beam or in case of plate girder, we usually check for the moment that is coming from the vertical loading. All right, and that's it. And in maybe in certain cases, combined effect of shear force and bending moment. But in case of gantry girder, you have to consider the combined effect of moments coming from vertical loading, and also moments generated due to the lateral loading. So in order to do that, you also need to calculate uh, certain, what can I say, certain properties of the section, in plastic moment of inertia, or sorry, plastic modulus of the section, in terms of both the axes, like z-axis, that is the normal axis when we calculate the section in terms of vertical loading, and also the y-axis, right? So that makes the problem a bit long, uh, but it's really interesting how we are going to design it. All right, so let's get started. So from the last class, from the last video, I just recapitulate a few things. We calculated, if you remember, you had a problem like this, and we calculated the uh, vertical loading, and along with that lateral loading, and the corresponding bending moments were calculated along with the shear forces. All right, so in this video we are going to start with the design of the preliminary trial section. So here you have a one simple thumb rule that we are going to apply uh, to calculate the depth of the section, width of the section. So these are the preliminary values, and L by 12 for the depth of the section, L by 30. These are the thumb rules, just to assume a value to start the problem with, and then use that value to actually obtain a section, right? So assuming this depth of the section as 600 and width of the flange as 300, you come to a approximate section modulus, right? In this case, this 1.4 that has been used, since uh, your gantry girder is different from plate girder, experiences loading differently from plate girder or beam. In certain cases there are combined effects as well. So 1.4 is just a factor of safety that we are going to take to enhance the section modulus, right? Whatever the loading there is, if it was a plate girder, you need not apply this 1.4, because you know that it is laterally supported, or it is not going to experience any extra forces from any other direction. But since you are designing a gantry girder, you already know certain lateral forces will be there, so you are just having some extra section modulus to safeguard your section against the combined effects. Okay, so if you can take it 1.4, 1.5 according to you, it's a simple assumed value to just enhance the section modulus. So you have a section modulus approximate value that can be applied in this problem. So based on that, we are simply going to take two sections, rolled steel sections, and put it together. Take a section like this, we'll have a I section and have a channel on top of it. So it is going to be a unsymmetric section. All right, so when we are going to calculate section modulus of unsymmetric sections, obviously it will require some rigorous calculations. So you take it from IS handbook 1 and then simply write down the properties. uh, it's all taken from IS handbook 1. You can simply go through that. All right, now after we take the sections, we are going to need to calculate certain parameters. Parameters like what is the depth of the neutral axis, right? Since it's an unsymmetric section, you have to calculate it. So here you have a calculation of depth of neutral axis from the top of the gantry girder, and then simply calculate the overall moment of inertia about z axis, and then calculate overall moment of inertia about this y axis. So this is there you have the z axis like this and y axis is like this. All right, and then after that you calculate the section modulus of the section, right? Now here the section modulus has been calculated in terms of the bottom fiber. Why is that? If you see, the depth of neutral axis is 247.59, that is this one, 247.59. So you see, from there the depth of distance of the bottom flange is quite high, that is 360. Now obviously it is understandable that you have a flange on top of this, so the neutral axis is bound to shift higher. But why we are going to take this section modulus about uh, bottom extreme fiber is simply because it is going to give me smaller value of section modulus. All right, the formula for section modulus is I by y, and so you have section modulus where I is greater, then you have a section modulus will be smaller, right? So and low value of section modulus, why we are taking this? Simply because we don't want our section to be overestimated, right? So if you are going to calculate a moment, we are going to take it as a by using a smaller value of section modulus. If you take a higher value of section modulus, we are going to overestimate the section, and then obviously under that condition the bottom section will fail, but the top will remain as it is, right? So we don't want any portion of the section to fail. So to be on a safer side, we are going to take the smaller value of the section modulus. All right, now coming to the next step, that you have to calculate the plastic modulus of the section. Now you already know how to calculate plastic modulus. It is basically calculated using taking moment of the area on both side of the equal area axis, right? So what is equal area axis? Equal area axis is basically an axis which divides the section in two parts. Top and bottom both are having equal axis, equal area, right? So simply you can apply this equation. They have tried this equation like calculating the overall area. They have assumed that at y depth the equal area axis is present, and based on that they have calculated top area and equaled it to the bottom area. So this simply represents that equation. If you just go through it, you'll simply understand. And finally, they have the depth to be 74.95 from lower surface of the top flange of I section. Lower surface means this portion, lower surface of the top flange. This is top flange, and lower surface is this one. From here, they have 74.95 mm length, depth, where the equal area axis is located. All right. So simply you have to now, if you want to calculate the plastic moment, plastic section modulus, you simply take the area of this section, multiply with the CG distance from the equal area axis, and then you have the section, plastic section modulus of this particular section. So they have simply done it. ZPZ1 represents the plastic modulus of the top portion, and ZPZ2 here represents the plastic modulus of the bottom section. So if you look carefully, you will simply understand. If you don't, let me know. We are going to obviously discuss it in the doubt clearing session. Okay, so I leave it up to you. Please don't overlook it, just go through the calculation, because obviously you need to understand this in details to do it by yourself. And finally, when you have plastic section modulus for the top portion and the bottom portion, you simply add it up to get the plastic modulus of the section for the whole sections, right? Then again you calculate the plastic section modulus for the y axis, that is this y axis, applying the same formula. In this case, obviously the section is the section is symmetrical about y axis, so it's a lot easier to calculate. You don't actually need to calculate the equal area axis. All right. Now, after we calculate the parameters like about ZZ and YY, the elastic section modulus, the plastic section modulus, all those parameters, when it's calculated, you're going to find out the section properties, that what kind of section are we dealing with here, right? So again, having studied the previous classes, uh, you know that how to do that. As per IS 800, there are guidance that is provided. You calculate the outstand of flange, you calculate outstand of the flange of the channel section, then D by TW, all these ratios according to the table provided in 800. You can simply classify the section, and in this case it is found out to be the entire section belongs to falls under the plastic category. Right. Now, since it's plastic category, you can calculate the local moment capacity by using this formula, which you already know. Simply ZPZ you have calculated previously, simply apply that, and also you calculate the limiting moment of the section as per the elastic section modulus. So if you see, this is your limit. The section cannot take beyond this point. So obviously in this case, the local moment capacity will be this value only, 1026.81. See, hence the moment capacity of the section is 1026.81, which is obviously greater than whatever load that is coming into the section, that is 676.16 kilonewton meter. Now again, you have a calculation about moment capacity about y-axis. Now why we are going to calculate that? Because we already know that there is a lateral load coming, and due to the lateral load, you will definitely have a lateral moment, right? The moment in the horizontal direction. So in order to do that, we already calculated uh, the plastic moment of inertia in terms of y axis. So you simply put that down, and along with that you have already calculated the section modulus, elastic section modulus in y axis as well previously. So simply taking that value, you have a limiting moment right here. So this is the plastic moment capacity, and this is the limiting moment capacity. So obviously your moment capacity about y axis is going to the limiting moment. Now, like I mentioned earlier, that obviously we are dealing with a problem where different kind of loads are coming together, right? So in that case, your section should be prepared to take all the loads simultaneously, and your section should be checked for the combined effect of these loads. In this case, however, we are going to consider the local moments coming from the vertical loads and coming from the lateral loads. So obviously you have two loads that is coming together. So this mz by dz ratio is basically mz is the external moment, mdz is the capacity of the section. Again, myf is the external moment due to the lateral load, and this is uh, obviously section capacity, and which should be, if you add it up, it should be less than 1. So if you simply calculate this, putting this down, this value, if you simply calculate, you'll simply find it to be coming out to be less than 1. So which is, that means your section is safe under the local moment capacity conditions. Now the next thing that we are going to do here is basically we are going to check for the lateral torsional buckling, right? So we already have done this step previously in beams, so it is quite simple, but there is one little thing that I'd like to point out. uh, if you if you remember, this was the step for laterally unsupported beams. This is your formula, and this is the step where you first calculate MCR, and then from that lambda LT, and then by calculating simply using these steps, you calculate ultimately the MD. So due to the section being laterally unsupported, there it may be possible that the section has some reduced moment capacity, right? Due to lateral torsional buckling conditions. So obviously in this case you are going to first calculate MCR as the expression is given here. However, this is given for only roll steel sections. However, in this case we are using a section which is built up where I section is there, and on top of it channel section is placed. So if you just simply read here, MCR for different beam sections considering loading, support condition and non-symmetric sections shall be more accurately calculated using the method given in Annexure E. So for non-symmetric sections under different loading condition, there are certain guidance given in Annexure E. So if you simply just find where the Annexure E is, this is your Annexure E. So, if you see this section, elastic critical moment of a section symmetrical about minor axis. So, in our case, the section is not symmetrical about major axis. However, it is symmetrical about minor axis. So, in this case, there is certain uh, constants that are given, C1, C2. So, simply we are going to apply this formula. Let's try to find out what is C1 here in this case. If you see this table 42, right? In this case, table 42, for different bending moment diagram and support conditions, the values of C1, C2, C3 is provided. Okay. So in this case, we have the section like the condition is given as it's simply supported in the both the support, both the ends, and the loading condition is UDL. So for that condition, for value of K, we have C1 equals to 1.132, right? So in this problem, a simplified version of that expression is used. Simply C1 is taken into consideration, not C2 and C3. So the whole expression remains same except one coefficient, that is C1. So C1, as I showed you, is taken as 1.132, uh, considering that the beam that the gantry girder is having an UDL on top of it. So uh, now simply calculate lambda LT, thickness, all those parameters you already have from the IS handbook, and simply by putting this value you find the value of MCR, and simply following the steps that you already know earlier how to do it. Simply by doing that you calculate the design bending stress, that comes out to 857.14 kilonewton meter, which is obviously greater than whatever that is coming onto the gantry girder. However, in previously we calculated the local moment capacity to be 1026. Now it is reduced 8 to 857.14 due to the lateral torsional buckling conditions. All right. Now, similar, similar thing. The beam is safe in bending under vertical loads. Since lateral forces are also acting, the beam must be checked for biaxial bending. Uh, so in this case, again, the biaxial bending. To calculate the biaxial bending conditions, first, uh, moment capacity due to lateral loading is calculated here, right? And then again the same formula is applied. The Here the moment from lateral buckling condition has been used, and then again it is coming out to be safe. So up to this point we have uh, taken a trial section. Using that sections we have calculated the sectional properties like uh, plastic section modulus, elastic section modulus for both the axes, major and minor axis. Then we checked for the local moment capacity. We took consideration of the biaxial bending conditions, and then again calculated the design moment considering the lateral torsional buckling condition, and then again uh, check the biaxial bending conditions. Now the next thing is we have to check for the shear capacity, how much shear will be coming onto the gantry girders. So as calculated previously, the maximum shear force due to wheel load is 377, and we already know impact load is taken as 10% of the wheel load, which is 37.73. So the total will be 41507, and simply applying this formula we can calculate the shear capacity of the wave. All right. So here we can see it is quite large than whatever coming onto the structure. All right. So now we have to check whether it's a high shear or low shear condition. So if you find it here, we have a low shear condition. So we need not check for the high shear condition, and no reduction will be there in moment capacity. Next thing that we need to check is for wave buckling, whether the wave will be able to take the load or not. Uh, Here again, for to check wave buckling, simply you apply the method you learned in case of beam or plate girder. All right, you find the bearing length, simply apply this formula, and then uh, check whether that particular load can be taken by the wave or not. All right, then the next thing that you need to do is to do a deflection check. uh, Simply applying this formula you can do that. uh, Calculate the deflection, and the whole expression how to do that is shown here. And we already discussed previously the permissible maximum deflection for manually handled uh, overhead crane is L by 500. So you have a limit of 16 millimeter to that cannot be exceeded, and in this case it's coming out to be 9.56, which is safe. Next thing that you need to do is to design the connections. The connections is to be designed considering the shear capacity in the mind, shear capacity of the weld. So the expression is there. If you can see, the shear capacity of the weld has to be calculated, VA y bar by IZ. Simply using this formula, you can see how much force will be coming, and then uh, we are going to provide a 3 mm weld size to connect the channel with the flange of the I section, and the strength that is provided by the weld is 331.39, which is greater than the required or the desired amount. So that is it. That's how you can simply design a gantry girder. It's a bit lengthy design process, so it is not that much recommended to attempt in the exams. However, it is very much interesting given the opportunity to explore different loading conditions and possibilities that come onto a structure. So that makes it very exciting to design in real life conditions. Okay, so this is where we end the video. I hope you liked it, and obviously following this there will be an assignment on design of gantry girder. So stay tuned.